Hello students, I am back with a new problem today. The problem is related to rotational mechanics. So this is my first video on the rotational mechanics. Here is the problem. A cylinder is released from rest from the top of an inclined plane of length L. As shown in the figure, what will be its speed once it reaches the bottom given that cylinder rolls without slipping? Okay, problem list 2 very simple. This is an inclined plane of length L and this is the cylinder which is uh, rolling and moving downward, okay, this way, and it is starting from rest. So the question is what will be its velocity when it reaches the bottom? When we say velocity, it is asking about linear velocity, right? Because it has rotational and linear motion both. So how do you approach this problem, right? So we can solve this problem in two ways. You might have guessed one is the, as usual, you can apply forces, you can draw the free body diagram, and then you can see what are the forces acting on, what is the acceleration, and then what will be its velocity once it reaches this bottom. The other way is apply principle of conservation of energy, right? Because all the forces are conservative, and since forces are conservative, the total energy of the system will remain conserved. So you can solve this problem two different way by applying Newton's laws of motion and then by applying principle of conservation of energy. In both way, you should get the same answer if you are solving it correctly. Okay, so what I'll do, I'll solve this problem the easiest way. You might have already guessed that easiest way would be the principle of conservation of energy. In this video, I'll solve this way and then I'll just make another small video in which I will solve the same problem using uh, Newton's laws of motion. Okay, I hope that will make your concept clear. So let's start. So approach one. Approach one. Principle of conservation of energy. Okay. So in this way, you don't have to draw any free body diagram and any those things, right? You will just have to see what is the energy initially and what is the energy finally, right? So total energy at the top will be how much? Potential energy plus kinetic energy. Any other energy you can think of? I guess there is no other energy here. So potential energy is what? PE is, it is at a height, right? It is at a height, some height from the ground. Height. This is height is h. So its potential energy will be let's assume that its mass is m. I think the mass is given in the problem. So I will just take the mass is given as m. Okay. So uh, PE will be PEI. Let's say initial potential energy initially will be mgh, and h is nothing but L sine theta, right? Mg L sine theta. Why? Because sine theta in this diagram is h by L. So h will become L sine theta. And Ke, initial kinetic energy, will be 0 because there is no motion. It is starting from rest. So total energy in initial energy will become mgl sine theta. Now final energy, total energy at bottom will be again PE plus KE, right? So now let's see PE final will become how much? Now it has reached to the bottom, so height is 0. So its potential energy you can just take as 0, right? What will be the final kinetic energy? Here is a catch. This has two motion, right? It is rolling. Rolling means it has rotational plus translational motion. So KE will be rotational plus translational, right? Assume that assume that velocity, final velocity when it reaches to the ground, at ground, velocity without that translational velocity, right? Or linear velocity, let's say. Translational velocity at ground equal to V. So rotational velocity omega will become how much? V by R, you know. Now let's see. So KER, kinetic energy will be half mv square, right? Sorry, first I read right ER, right? So let's write first this KER. It will be half I omega square plus half KE is half mv square, and then how much it will become? Let's put the value. What is the what is I here? I is the moment of inertia about the center, about an axis passing through the center of the cylinder, right? So what is the value of I? I know, I guess you already know what is the value of I here. It will be mr square, assuming assuming r is the radius of the cylinder. See, in the problem radius is not given. So what you can guess is r will finally will vanish in the final result. So let's assume for now that r is the radius and it will go away. So half is already there, and then I is half mr square. This is I, right? And then you have omega square. Omega we already know that r, v by r square plus half mb square is the kinetic energy. How much it all uh, adds to? It will become mr square v square divided by 224 r square plus half mv square. R square, you know, you can cut, right? So r vanished now. Now let's see how much it will become. Mv square, let's take common, which will become 1 by 4 plus 1 by 2. This will become mv square. This is plain mathematics. 4 you can take LCM, it will become 1. This will become 2. So this will become 3 mv square by 4. Okay. So this is the final energy. Final total energy is UF will become PEF plus KEF, 0 plus 3 mv square by 4. Now from principle of conservation of energy, since system is conservative system, all forces are conservative forces here, conservative system. So apply conservation of energy. Ui will become UF, and Ui we already found how much? mgl sine theta. So mgl sine theta equal to uf 3 mv square by 4 by 4. M and M you can cut from both sides. This will give what? V will become 4 by 3 GL sine theta under root. And this is your final velocity once the cylinder reaches to the ground. Okay, it was easy, right? We just had to think about rotational plus translational motion. Once you see it, this hidden motions, and then once you write it correctly, all your problem is solved and you got the correct answer. I hope you learned from this problem how to attack a problem and how to analyze a system. In the second part, I'll create another video where I'll solve the same problem using Newton's laws of motion and kinematics. Okay, bye bye.